I welcome everybody to this fantastic day. Enjoy.
Thank you, Dr. Luis. Thank you very much for the nice welcome speech. I hope you enjoy the rest of the program. Thank you.
All right.
Next, we can start the keynote session, and I would like to hand it over to my colleague, Dr. Michael Langberg. Mike, take it away, please.
Okay, thank you. Thank you very much. So hi, everyone, again, and welcome to the third Buffalo Day for 5G and wireless IoT. I'm Michael Langberg. I'm a faculty at the EE department at UB, and I specialize in the area of information theory. It is my great pleasure to introduce the first keynote speaker of today, Tommaso Melodia. Tommaso is the William Lincoln Smith Professor with the Department of Electrical and Computer Engineering at Northeastern University in Boston. He's also the founding director of the Institute for the Wireless Internet of Things and the director of research of the Power Project Office. Tommaso's studies started at the University of Rome, La Sapienza, and continued at Georgia Tech, where he received his PhD in 2007. Tommaso knows UB and our department very well, as we enjoyed having him as a faculty member in the EE department for several years before his move to Northeastern. Tommaso is an IEEE Fellow and recipient of the NSF Career Award. He's currently serving as editor-in-chief for Computer Networks, and he served as associate editor for IEEE Transactions on Wireless Communications, IEEE Transactions on Mobile Computing, IEEE Transactions on Multimedia, and more. Tommaso's groundbreaking research focuses on modeling, optimization, and experimental evaluation of Internet of Things and wireless network systems. And today he's going to be speaking on AI-based control and orchestration in the Open RAN, architectures, algorithms, testbeds. So Tommaso, thank you very much for joining us. It's a true delight to have you with us today. The floor is yours.
Thank you very much, Michael, and thank you to all the great friends at the University of Buffalo. I want to thank Jang Yu for inviting me, and all the other organizers for inviting me. University of Buffalo, Florida Atlantic University, lots of friends, lots of great memories there. So it's truly a distinct pleasure to be here. I only wish I could be enjoying the pre-Thanksgiving season in Buffalo, but we'll do it next time. All right, so can you see my screen? Yes, I think you can. Wonderful. So today I'm going to be talking about work that we've been doing, I'd like to say, over the last 3 years, that has to do with a new networking paradigm, the Open Radio Access Network, and how we can leverage new AI-based control techniques and inference techniques to control and orchestrate the Open RAN. And we're going to see a lot of different elements that make this possible. So we're going to be talking about architectures, algorithms, and testbeds, although I may leave the testbed part a little bit for the panel discussion that we're going to have later today. Okay, this is work that has been made possible by a lot of different people, PhD students, postdocs in my group. I'd like to acknowledge all of them. Without their hard work and the cooperative environment, this would not have been possible. Okay, so what are some of the main limitations today of existing cellular networks, the cellular networks that are deployed in the field? They're by and large based on what we call monolithic architecture, sometimes called black box architecture. They are hardware-based, and all the functionalities are implemented in hardware and intertwined within the hardware fabric, which makes them in many ways hard to update, improve, introduce new functionalities, reconfigure. This leads to major capital expenses every time that you need to move from one generation of a network to the next generation of a network. It results in security challenges. Also for the industry, it results in something that is known as vendor lock-in. Because of the proprietary nature of all this network equipment, if you deploy a radio access network in a certain area with equipment from a specific manufacturer, all the equipment needs to be from that manufacturer. And that clearly limits innovation in the field. It also makes it hard for a network operator to control in a programmatic way the behavior of the network, especially over large scale. There is a lot of manual configuration that goes into deploying and optimizing a network. And there is a growing gap between what we know in theory about how to optimize the behavior of a network and what we can actually do in a real deployment. Okay, so researchers like me and many others have been developing over the years a lot of very sophisticated network optimization techniques that cannot be implemented in the field. Okay, and this results in the fact that it becomes very hard to support increasing traffic demands. You need to come up with completely new generation of networks, etc. There's something that has happened in the world of enterprise networks over the last few years and in data center networks, clearly, that is referred to as software-defined networking. So there's two main ideas in software-defined networking. One is the idea to separate the so-called control plane of the network from the so-called data plane or forwarding plane, okay? So separate the logic that controls the behavior of the network from the actual execution of certain functionalities. The second big idea, and in my opinion, the most important idea in software-defined networking, is the idea of exposing network control functionalities through a centralized abstraction of the network, right? The whole general idea in networking was you have a bunch of different routers are forwarding packets, and you write routing algorithms that are executed on each individual router, and the global network behavior is given by the interaction between the distributed algorithms that are executed at each individual router. In software-defined networking, this paradigm is shifted, and you have a centralized abstraction of the network through which you program the overall network behavior, and that is implemented by means of specific protocols on the various routers. So that's a very major change in how we think about networking. And it has happened for the next 10 years. The other big thing that's been happening is what we refer to as network function virtualization, right? And it's the idea of separating, virtualizing network services and functionalities by separating, decoupling them from hardware. So you have now a network function virtualization infrastructure that includes physical hardware with virtualization layer that can be obtained with several different technologies. The virtualization layer supports virtualized network functions that are executed in software that provide the various functionalities that are needed in the network. All right, this is all by and large happening in the wired world. What's happening in the wireless world? Evolution in the wireless world has been a little slower, but it has taken a major acceleration in the past couple of years, okay? We've seen decisively a move towards something I like to call vertical disaggregation, right? The traditional approach is you have your base stations with a hardware monolithic base station that you put on top of a tower. And now we're moving into a world in which you have a white box base station, open and programmable base stations that are connected to servers that execute in software most of the functionalities that were in the past implemented in the hardware of the base station. Okay, this is something that has taken very different names. Sometimes it's called Cloud RAN or Cloud Radio Access Network, Virtualized RAN, C-RAN, various different names. But it's distinctively it's the separation between software functionalities executed in a virtualized environment and the base station that becomes a programmable software-defined radio. The other thing that has been happening in the past couple of years is what I like to call horizontal disaggregation, okay? And the industry is calling this also horizontal disaggregation. So we're moving from a situation in which you have a traditional black box hardware with all the functionalities implemented in hardware, from the physical layer functionality to the baseband processing, radio resource management, etc. all of these functionalities are moving to a set of disaggregated entities that are run at least partly in the cloud. Okay, so we have something that is called the OCU, something that is called the ODU, and something that is called the ORU. The RU is the radio unit. It basically contains the low physical layer functionalities, some of the baseband processing functionalities, specifically things like FFTs, beamforming, etc., and basically all the functionalities that are needed to generate the radio frequency signal and transmit them or receive them over the air. Through standardized interfaces referred to as open fronthaul, the ORU is connected to an entity called the ODU, or distributed unit, which is in charge of most of the baseband processing functionalities. The ODU can be implemented in hardware, but it can also be implemented as a virtualized entity in the cloud or at the edge of the network, with the idea that the distributed unit, because it processes baseband samples, needs to be somewhat close to the radio unit, physically close. By means of another standardized interface, you connect the ODU to something known as the OCU that is in charge of some of the slightly higher layer, link layer, radio source control functionalities in a network. And then, last but not least, all this disaggregated base station, disaggregated infrastructure is connected to an entity that is known as the RIC, or RAN Intelligent Controller, right? The RAN Intelligent Controller, very much like what we described for software-defined networking, is an entity that abstracts the network and exposes, by means of a set of, let's call them standardized APIs, all of the metrics that are generated by the various disaggregated units in the network, as well as it exposes the ability to control in a fine-grained way the various units in the network. Okay, so now on the near real-time RIC, you can write applications known as XApps that can control in real time or near real time. We'll talk about timing issues in some detail, the behavior of the network in a programmatic way. And this can be, from the network operator perspective, third-party applications that run standardized substrate and have access and can control different entities in the network. Okay, you see very clearly that this will make a cell network and radio access network look very different than what we had in the past. So we're moving to what we call open, programmable, and virtualized wireless systems. They're open because the interfaces are open and standardized. So the OCU and the ODU can be provided by different manufacturers, right? They're programmable because of the RAN Intelligent Controller. So you can write applications that will control the behavior of the network, and you can program the behavior of the network and offer new bespoke services based on demands. And they're virtualized because large portions of these are executed in cloud-native environments. All right, I talk about this open architecture, specifically the ORAN Alliance is an industry-led consortium, operator-led consortium that is trying to standardize the Open RAN architecture. It's basically doing two main things: standardizing the open interfaces, so all the interfaces that create the boundaries between the various different units. And it's also defining and standardizing the RAN Intelligent Controllers, or RICs, right? These entities over which you can program the network. And specifically, there's in the ORAN standardization bodies, there's two main things that are happening. The near real-time RIC, which is in charge of controlling operations that have timescales between tens of milliseconds up to 1 second, and the non-real-time RIC that is in charge of service management and orchestration functionalities that have timescales in the order of several different seconds or more. All right, so the vision is, I think we're moving towards an end-to-end programmable virtualized architecture. What's Open means many different things. Like at the minimum, open means that the interfaces are open and that there is well-defined interoperability between the various different entities. Open also can mean based on open source software. That's not a mandate in anything that the Oran Alliance is doing, but there's a lot of very interesting activity in the world of open source software. As of today, you can already find software framework through which you can implement an end-to-end virtualized software network by means of open source frameworks. From the user equipment to the to LTE base stations that are available today, 5G base stations are available today through open source software. Open source software is available for edge cloud, for intelligent controller, for core network, and for management and orchestration functionalities like network slicing. And clearly there is still a lot of evolution ongoing. The robustness is often not to production levels, but this is evolving in a fast-paced way, and there is no doubt that there will be major advancements in this field. Now, if you look at this architecture, clearly this openness and softwareization of the architecture opens up a number of very interesting opportunities for research and specifically for intelligent inference and control based on artificial intelligence algorithms. So you can think of applying artificial intelligence to control functionalities on specific mobile devices, right? To do things like real-time waveform-based adaptation by controlling directly functionalities on the mobile device itself. You can use artificial intelligence in the radio access network to control functionalities like scheduling, mobility, access, etc. You can use artificial intelligence at the edge of the network for optimization of the RAN, caching, providing intelligent edge services, and the like. And you obviously can think of artificial intelligence applied at the core for things like orchestration and slicing. So at Northeastern, in a group in the past few years, we've been working on, I would say, all of these potential applications of AI in the open radio access network. And we're going to talk about some of them. Now, specifically, if we look at the Oran architecture that you see here on the right, and you look at the various control functionalities that exist in a network, right? You can think of creating a number of intelligent control loops, right? Where you take, these are basically sequential decision-making engines that control the behavior of a number of functionalities based on information that is exposed and made available by various parts of the network. And clearly, they differ in terms of the scale, the number of devices that they control, in terms of the specific input data that is necessary to control that specific functionality, and in terms of the time scales, right? So, for example, Oran, the current Oran specification already support a number of different intelligent control loops. So you have control loops between the so-called non-real-time RIC and the near real-time RIC. That control functionalities that can have time scales in the order of several seconds, controlling functionalities like policies, long-term policies, network slicing, and the like. You have control loops between the near real-time RIC and the CU, right? That control functionalities like user session management, load balancing, handover, etc. These have time scale in the order of tens to hundreds, more likely, of milliseconds. You have control loops between the near real-time RIC and the DU, control functionalities like scheduling policy, RAN slicing, the number of PRB utilized, and these are again near real time, so orders in the orders of hundreds of milliseconds or less. There's a number of control loops that are not supported by ORAN today. I believe they will be supported in the future because they enable a number of crucial control functionalities that include radio management, things like resource scheduling on a fine scale, beamforming, etc. These require control loops that require acting specifically on the digital samples, on the IQ samples in the network. So the decision needs to be taken close to the functionality that you're controlling because of the real-time nature of these functionalities. And so this will have to be probably executed closer to the base station on the DU itself, if not on the RU. And this is something that is not currently supported or standardized by ORAN that we'll be advocating for. Okay, so let's start looking at a few examples. We talk about the fact that we can have AI on specific mobile devices. We've been working on a number of different programs at Northeastern. One of them is the RIF-MILS program supported by DARPA. RIF-MILS is trying to do primarily a couple of things, but the main idea was to develop artificial intelligence algorithms. And in our group, we have specifically used convolutional neural networks to basically be able to fingerprint devices that are identical from a hardware perspective, but can be, in fact, identified by means of neural networks. So imagine you have, in its simplest form, you have two different devices, right? These devices are identical from a hardware perspective, and they're transmitting bit similar signals. So they're transmitting the exact same bits, right? The waveform are slightly different because the hardware that is transmitting while being nominally identical has imperfections, right? The power amplifiers, the antennas, they're not exactly identical. So they introduce different impairments on the signal that is being transmitted. Right, so the challenge of the DARPA RIF-MILS program was, can you recognize different devices by observing their waveforms as received at the receiver, sending them through artificial intelligence engines that should tell you this was transmitted by transmitter 1, this was transmitted by transmitter 2, right? And then, generalize that, do it with tens of devices, do it with hundreds of devices, do it with thousands of devices that are bit identical, right? So we've been doing quite a bit of work on this space, and you can find quite a bit of information on our website, on the website of my co-PIs on this, Kaushik Chaudhary, Stratis Ioannidis, and Jennifer D. But I think what was very interesting to learn is, yes, you can use convolutional neural networks to identify different devices. And in fact, what happens is that if you train test with information from one day, you can get levels of accuracy that are very high, right? But now, if you train with data taken on one day, and then you test with data taken on different days, the performance decreases significantly, okay? And that is because the problems that we're dealing with here are quite different with respect to, classical computer vision problems where AI has been working very well, and that is the fact that the wireless channel changes significantly over different days and introduces impairments that are varying in time. So you need to find ways to generalize and remove the effect of the wireless channel. We've been developing a number of techniques to do that. I'm not going to go to a lot of detail that include filtering before sending the information to the convolutional neural network to remove the effect of the wireless channel, data augmentation techniques to generalize the training and reduce the effect over different days. And these have resulted in results that are quite interesting and very promising. I believe that there is a lot of work to do on AI inference over wireless channels in practical settings, and this is an area where we will continue to work over the next few years for sure. Another interesting idea, and this is something that we've been developing with sponsorship from the Office of Naval Research, is the idea of polymorphic communications. What's the basic idea of polymorphic communications? Is imagine you have a receiver that is receiving a waveform, and now the receiver is not explicitly told by the transmitter what are the parameters that the transmitter is using for a specific waveform. Now the receiver can infer the parameters of the waveform by means of artificial intelligence engines that observe directly in real time the stream of IQ samples that is received at the radio, reconfigure in real time the behavior of the receiver to be able to receive these different the different waveforms, right? So imagine now you can design a transmitter-receiver pair in which the transmitter is continuously adapting the behavior of its waveform without the need to inform the receiver, right? Maybe because it doesn't want to inform the receiver, it doesn't want to be eavesdropped and doesn't want to be jammed, or simply to save on overhead, right? And the receiver is able to in real time infer the parameters and adapt its receiver to receive correctly that packet. This is something we've implemented and tested with the logic of what we call polymorphic receive. And the idea is you have software radios with radio frequency front ends. The front end sends the stream of IQ samples to a basically core on FPGA, executed on FPGA, that sends then the IQ samples to a neural network executed on FPGA. Neural network has been trained to recognize the parameters of the waveform, and then can reconfigure in real time a receiver logic that can tell the receiver what to receive. Not going to go into a lot of detail, but we have basically created a library through which you can define at a high level in Keras the parameters of the neural network to receive the space, and then this library automatically creates basically FPGA implementable code that can execute your receiver. And by doing this in FPGA, we've been able to demonstrate with respect to pure software implementation on embedded systems, 15 times reduction in the energy consumption and 17 times reduction in the amount of latency. And this has been demonstrated in prototypes. What you see here is a receiver that is continuously switching, learning to identify the number of FFT points in an FDM transmission. So the transmitter changes continuously between 64, 128, and 256 FFT points, and the receiver automatically identifies that and is able to receive. Obviously, proof of concept can be generalized in many different ways, but that's the idea. Few other applications. You can think of AI to control functionality that are relevant both to mobile devices and in general to the radio access network. An example of that is 5G millimeter wave transmission, right? Which are characterized by specifically directionality, high data rates, so very large number of IQ samples that need to be processed, and the characteristics of blockage, right? Typically, one of the main problems in millimeter wave lengths is that they're directional, right? Because they're directional, you need to be able to align the beam between the transmitter and the receiver and maintain alignment between the beam, right? Especially initial access is a problem, right? When a new device joins the network, the device doesn't know where the base station is located. The base station doesn't know where the device is located. So it takes some time to coordinate transmission between the base station and the transmitter. And AI clearly can play a crucial role in optimizing this procedure. So here's how it works normally. So you have a base station and the receiver. There's a number of different potential beams that are available to the base station, a number of potential beams that are available to the receiver. You do something that is called exhaustive beam scan, right? Where periodically the base station is transmitting pilot bits. These pilot bits are used for beam management, and it takes a significant amount of time to be able to exhaustively scan all the possible combinations and identify beams that are aligned between transmitter and receiver, right? Now, what would we like to do, right? We would like to use artificial intelligence to do two things. Identify basically the angle of arrival between a transmission from the base station to the receiver, right? And identify what beam is being used by the transmitter, okay? If I know what beam is being used by the transmitter and the angle of arrival, then I can immediately align my beam, right? And I can do it even on the same packet, right? I can start looking at the preamble, identify what beam is being used, the angle of arrival, and immediately switch the beam to be able to receive correctly the signal without the need for coordination, okay? Without the need for a specific exhaustive scan. And so we have developed this framework, DeepBeam, which we presented earlier this year, which tries to do exactly these two things, right? So it looks at IQ samples at the receiver, as received by the receiver chain. In FPGA, with a very efficient and fast implementation, runs a convolutional neural network that are able to identify which beam is the transmitter using, right? And what is the angle of arrival from a discrete set of possible angle of arrivals. And then adapt the specific beam to maximize the performance of the link. We've, I'm not going to go into a lot of detail, but the results are quite promising. They've been obtained by collecting a very large amount of data at 60 gigahertz. So we've used two different setups, side beam, which is a phase array connected with the NI PXI chassis. So it's a software radio at 60 gigahertz with an analog phase array. And a second set of radios developed by a startup in New York City called Pi Radio that develops an SDR with digital beamforming, again at 60 gigahertz. Collected data set, trained the neural network, implemented the neural network on FPGA, did a lot of experiment. And you can significantly, you can have very high accuracy, order of 90% in identifying correctly the beam and angle of arrival with low energy consumption and very much reduced delay with respect to the classical 3GPP initial access procedures. Few other examples, DeepSense. DeepSense is something that we've worked on earlier this year. It's the idea of using, again, convolutional neural networks in the RF chain, so directly on the IQ samples to identify available spectrum bands. So you can think, for example, of a receiver chain that is receiving a waveform. Imagine, for example, in a Wi-Fi environment, the IQ samples are run through a deep neural network. They identify which specific bands are being used and which specific bands are not being used, and can reconfigure directly the baseband processing module to transmit your signals on the bands that are not being used. So think of a very fast adaptation of the link to continuously use the specific frequency bands that are not being used at a certain time. Okay, so far we talk about AI specifically used on mobile devices in isolation or in coordination with functionalities in the radio access network. Now, clearly AI has a lot of applications for controlling the behavior of the network overall and the radio access network specifically, right? An example of this is work that we've been doing for intelligent scheduling and slicing in a radio access network, right? So one of the big promises of 5G is this idea of slicing, so of creating a virtualized network that sit on top of the same physical structure, right? You have heterogeneous traffic demands, and so you can think of having coexisting slices for traffic with different characteristics, massive type communication, enhanced mobile broadband communications, and ultra reliable and low latency communication, different slices, right? With dynamic channels, that can be diverse and vary with time, and you want to have dynamic resource allocation in each slice to provide the behavior that you want to obtain in each individual slice. So yeah, what we wanted to demonstrate is the ability to use data-driven closed-loop control implemented in the near real-time rig, as I described earlier, to automatically tune, control the parameters, the run parameters on each slice, okay? And specifically in this initial work, we've been focusing on controlling two main things. Number one is for each slice, selecting a specific scheduler to be used from a discrete set of available schedulers. Obviously, this can be generalized. One could have the AI invent the scheduling policy. We haven't done that. We've just selected the scheduling policy from a discrete set of available scheduling policies. And the second thing, we want to be able to size the slices in real time. So assign a certain number of resource blocks to each slice to be able to control the behavior of the network. Okay, so as I mentioned before, the way you implement intelligent control algorithms in Open RAN networks is by means of so-called XApps, right? So the XApps are deployed at the near real-time rig. They're executed in the near real-time rig, which is going to be somewhere in the near real-time, in the regional cloud, and interacting with the CU and DU implemented in the edge cloud by means of the E2 interface, okay? And the XApps are those that implement data-driven, in this case, sequential decision-making algorithm that will control the behavior of the other entities, right? Now, a specific provision of ORAN, as of today at least, is that you can't do online training, or you can't do a significant amount of online training. So you have to deploy XApps that have been pre-trained offline based on data, obviously, that can be collected from a live network, okay? So the model needs to be trained beforehand, and you need a lot of data to do that, okay? You need data from large-scale deployments. There has to be created under different conditions, mobility, traffic, etc. And obviously, telcos are not very eager to share their data, new oil, right? So we need to, as a research community, to advance in this area, we need to create something we've been calling open wireless data factories, or smart RF data factories. One of them is certainly Colosseum. Colosseum is, sure many in this audience will be familiar with Colosseum, but some may not, so I'm going to spend a couple of minutes talking about it. Colosseum is basically a data center, but it's much more than a data center. It's known as the world's largest radio frequency wireless simulator. It includes 256 software-defined radios, USRP X310, 21 racks of servers that include the radios, a very large fabric of FPGAs, very large number of servers. We have recently added 3 additional servers that contain additional AI computational functionalities. So we have a very large number of GPUs and a bunch of other radios that we're using for development, just basically to create the future versions of Colosseum. So the radios, what's quite unique is that all of these radios are connected with servers that can virtualize the protocol stack, as we have described, right? So you have very large computational power and one-to-one connections between servers and radios. And then you also have a large fabric of FPGAs that can create a mesh connecting all of the radios, right? All of the different content of the radios. And you can program these FPGAs to emulate very complex channel scenarios in which you can, in real time, emulate all the interactions on the wireless channel between these 256 by 256 channels, right? So whenever a radio transmits, all the other radios receive, if you program your emulator to do that, attenuated, distorted versions of the signals and the sum of the transmission from all the other signals. So very complex spectrum sharing scenarios, very complex network scenarios can be emulated in Colosseum. So clearly Colosseum is can enable doing experiment with virtual worlds and with collecting very large amounts of data from realistic scenarios. So we have integrated an ORAN architecture in Colosseum. Imagine, so in the specific scenario that I'm describing here, we have created in Colosseum a scenario that models the actual physical area where the real Colosseum is, just for fun, so to speak. So there's 4 base stations. We've taken the location of base station from the OpenCell ID, and there's approximately 10 users in this example here that are connected to each base station. So we have 4 base stations, 10 different users per base station. There's 3 different slices implemented at each base station. Slice for mobile, for MTC traffic, ultra reliable low latency traffic, and enhanced mobile broadband traffic. And then you have the various UEs, right? The users. The UEs are implemented with the SRS run software on specific software radios. And then the base stations are implemented also with the SRS run software for specific base station. Then we have created a containerized infrastructure that includes all the ORAN architecture. We have basically a non-real-time rig where we do the offline training. We have a container that implements the E2 termination on the near real-time rig. And we have created the termination on the base station to be able to interact with and control the software on the various base stations. We have a rig database implemented as a different container, and we have XApps implemented as separate containers. So we have containers with XApps controlling each base station, and we have basically a controller for each base station and a controller for each slice. So 4 base stations, 3 slices, we have 12 different controllers, deep reinforcement learning controllers. Okay, so in the non-real-time rig, we do the offline training and the storage of the model. The near real-time rig runs the XApps, and it has all these various components, E2 manager, rig database, etc. And then we had these different deep reinforcement learning aids that were trained offline with 63 hours of experiment. So we basically run, we let Colosseum run for a long time, generating data that looks at different configurations with different mobilities, different parameter configuration, observe that in real time at the base stations, record some aggregated data of the performance of the network, right? And then train the deep reinforcement learning agents based on this data, okay? And then run the agents in parallel. I talk about the specific scenario. I'm not going to go into too many details, but selecting the scheduling policy between round-robin, water filling, and proportional fair scheduling for each base station, and also assigning the number of resource blocks for each slice. So that's the control problem that we're looking at. Results are in a couple of papers. One is already available. The other one will be made available soon. But this is already showing very promising results. This shows the spectral efficiency CDF for the various different scheduling policy with respect to the DRR control, and clearly we can get a 20% gain with the adaptive scheduling with respect to using a fixed scheduling policy. In ultra reliable low latency slices, we can reduce the downlink buffer occupancy by 20% in average, which is also quite promising. This is, I'm not going to go through, what time is it? Not in the interest of time, I'm not going to go through the video. If you're interested, I'll be glad to send you a link to the demo that we presented at the Mobile World Congress 2 weeks ago. That demonstrated ORAN in Colosseum with an AX-based network slicing and resource scheduling. It's an interesting video going into a lot of more technical detail than I was able to do here. Last thing that I wanted to mention, and then I'll conclude, and this is something that we've been working on in the past year, and we'll continue to work on this over the next few years. It's something that it's of great interest to us, and it's the idea of creating zero-touch orchestration for cellular systems. So the idea is to be able to control the behavior of the network by defining the operator's intent at a very high level, right? Something like, I need to be able to stream 4K video to 100 users in Times Square, New York, from 8 p.m. to 9 p.m. Define that high-level language, ideally natural language, and then have orchestrating intelligence across the network to be able to collect the data that is needed to train agents, and then deploy the control action and the software in various parts of the network to be able to provide the service that is required by the operator in a zero-touch fashion. Coming soon, we haven't released any specific results on this at this point, but we're hoping to be able to do that pretty soon. And this concludes what I wanted to cover today. And I'll be talking a little more about testbeds later today in the panel. If anybody is interested, then I'll be very glad to take any questions if there's any.
Great. Thank you very much, Tommaso, for that great presentation. So we have some questions in the chat, and I'm inviting people to open the Q&A tab, which can be found through the 3 dots on the right-hand lower corner of the screen, and you can ask questions. So what I'll do is I'll read the questions out loud, and Tommaso, if that's okay, you can answer. You may be able to see them also on your own. I'm not sure if it's.
Sure, I'm not seeing them, but Mike, if you could read them, that'd be wonderful.
Sure. So we have, for our first question is from Sastri Compera. Has there been any buy-in from the carriers to implement ORAN architecture, as they're usually risk-averse and want complete lock on their entire operation?
Right, very great question, Sastri. I think my impression is that carriers are somewhat bullish on Open RAN and quite open. Primarily, and it is true that they're risk averse. They're probably thinking about ways to reduce their risk, but they're also very much cost averse. And this is something that can, there's studies that show reductions in capital expenses of 50% already in early deployments of Open RAN. Rakuten specifically has declared that they're building really cloud native Open RAN network, and they have at this point already declared that they are able to reduce their capital expense 50%, and I believe operational expenses by 30%. So that's huge for them. Manufacturers obviously are more reluctant for obvious reasons, but I think in many ways they're also positioning themselves. They think that this is going to happen one way or another. It's inevitable, so they better be positioned to be players in that in a different way, maybe from what they have in the past. And I think this will primarily at the beginning happen in private network deployments, and then it will trickle down to probably to larger deployments. But some forecasts are saying already by 2027, 50% of the deployments will be based on Open RAN architecture. So I think it's happening one way or another.
Great, thank you. So another question, I think they're coming in pretty fast. So by Michael Seguin, for the beam management, why can the packet header or footer data not include the GPS location and angle? Then there could be some closed loop control to align the beam based on the location.
I guess you could. That's for sure another way to do that. There's, however, lots of operations that don't happen in areas where GPS works. There's devices that don't have GPS. So I think there's obviously a lot of interest in creating solutions that are not GPS dependent. But GPS certainly is an option. Also, you have an issue of precision sometimes with GPS, right? Especially in indoor deployments, and mid-wave will be deployed, indoor to a significant extent, at least at the beginning. The precision of GPS indoor may be limited, but that's a great point. I mean, it's another great way to do that.
Thanks. There's a question regarding the last topic of zero touch, and maybe it's a request to add a little bit more details. So zero touch can be an important feature for next generation networks. How to understand zero touch capability? Are there any specific indicators?
Can maybe whomever asked the question comment? What do you mean with indicators? Sorry.
Yeah. If you can elaborate on the question chat, then or in the Q&A, I'll ask the more elaborative question. Maybe we'll move on to the next one, and then we'll get back to that one if that's okay, until I get the answer.
Sure.
So R. Tarbell is asking, in terms of XApps, can you have an example of a most demanding process that requires firm real-time resources?
So everything that has to do with adaptation that happens at time scales in the order of a few milliseconds require hard real time, right? So hard real time, it's something that, think of that, tens of seconds, right? Something like that. So if you look at the slide where I described the various intelligent control loops, right? Adapting modulation, interference blockage detection, all these things have time scale that are real time. Radio management, things like beamforming can be in the order of tens of milliseconds. As of today, you can't do this with ORAN, right? So ORAN assumes that, and in fact, ORAN correctly calls the RAN intelligent controller near real time. This is something that can have access to information from the DU, but it doesn't have access to the IQ samples. And if it had access to the IQ samples, it would be delayed, right? So for something to act those time scales, you need to execute the intelligence on the DU and on the RU, or on the RU. So it wouldn't really be an XApp. The XApps are run on the near real-time RIC. It would be something that, in an unpublished paper that we've written, we called these D apps, right? Apps that would need to be executed on the DU and that could control functionalities that have this time scale. I believe we're going to propose to the ORAN Alliance to introduce formally the apps. We haven't done that yet, but we've been studying how that will work, and this is something will be needed if you need the real-time control. I hope that answers the question.
Great. So we have 2 follow-up questions. We still have time. The next session is 6 minutes away, so yeah, I hope that's okay. And so we have 2 follow-ups. One from Sastry, of course, thanking you very much for the answer, and asking to elaborate more on the trade space between computation, communication, and storage when it comes to network slicing at the edge.
Okay, that's a tough question. And Sastry, I'm going to send you a paper that we have published last year just on this topic. We called it SLEDGE, or network slicing at the edge. So we tried to develop a model there. This is a paper that is mostly theoretical. It has some experimentation as well, but it's primarily theoretical. And it tries to say, okay, well, if you're doing slicing, you have to look at not only the communication functionalities, right, which is what most slicing papers, at least from our community, are looking at, but you need to also look at the computational capabilities that are needed and the storage capabilities that are needed for a specific service. For example, if you're trying to provide the slice that is doing video transcoding, right, you need to have computational capabilities that can, in real time, do can change the encoding of the video, right? And you can't ignore the fact that when you're doing slicing, you can't ignore the fact that computation, slicing, and storage functionalities can be coupled. So you have to include all these 3 dimensions in your slicing. And we propose models and algorithms to do that in this paper, and I'll be glad to send it over to you, Sastry.
Good. Thanks. The next one, the question is again a follow-up from Michael Segwin. NVIDIA has a CUDA interface to help machine learning in the E2 RIC protocol by moving code from the CPU to the GPU. Do you see Colosseum supporting GPU allocation in the future? So
Colosseum does have GPUs in 2 different ways. So each individual server that controls the various the various radios has multi-core CPUs, and it also has a GPU. The GPUs are not really, so they're like 3 years old, so they're not really the state of the art, but they're still quite useful for online inference on each individual device, so to speak. There's also a very new instead rack that includes NVIDIA A100 machines, so that's really the best GPU servers that you can think of, and this is available today on Colosseum, so you can do that that kind of training. And you can use that for inference, so you can offload computation on those, and so it is already available now. Not super easy to use, but it is available.
Great, thank you. So maybe the last question, I'll give a question of mine. We have something like 2 minutes until we have to hand off to the next session. So this framework has so much potential for innovations. It's really inspiring, and I was just wondering if what kind of studies have been done regarding privacy and security using these techniques.
I think this is I am losing my voice. Great question, Mike. There's a lot of interest in privacy and security in the Open RAN for sure. There's, as you correctly pointing out, there's a lot of interest. I am aware of white papers that exist that look at these problems. It's not really technical papers. So Ericsson published a white paper on security in ORAN maybe about a year ago. What are some of the research challenges to highlight to secure the Open RAN? There's, as you can imagine, it's a new framework that contains architectures and specifically interfaces between different components. So you need to secure those interfaces. And there's also algorithms and potentially third party that can be introduced in the network. So you need to secure those algorithms as well. You need to be able that they're based on the data that they think they're based on, if they're data-driven algorithms. And you need to be able that the behaviors that the control behaviors that they implement in the network are correct, right? And not only that, there's also lots of consistency, right? You may have different XApps running in parallel in the run, and they may be trying to control the same device. Or you could have internal control on the device that is conflicting with the external control that come from the running controller. So there's a lot of interesting problems to be studied in this space, and I think we're just scratching the surface in many ways.
Okay, I want to thank you again for the excellent presentation. Yeah, so we can't clap hands, but at least virtually. And I hope your voice later on you can rest a little bit. Good. So I'm going to hand this off to the next session chair, Xiaofeng.
Hello, can you hear me?
Yes, we can.